Directable motion retargeting through motion paraphrasing. In this work, we tackle the problem of motion retargeting through the lens of motion paraphrasing. Given a source motion, the goal is to retarget the motion to a new character while maintaining high-level semantics. However, this is an under-constrained problem. So, similar to text paraphrasing, we also want to allow for natural variations in the low-level details of the motion, for example, small limb movements or step length. To address this problem, we introduced DMP, a novel motion retargeting framework for directable motion paraphrasing. Given a source motion, our approach generates a range of possible retargeting solutions that capture natural variations in movement. DMP also provides intuitive user control over retargeting through kinematic constraints. In this example, the route trajectory of outputs are constrained to match the source motion. Constraints also enable realistic scene interactions. If we add a ceiling into the scene here and add a collision avoidance objective to retargeting, it forces the taller character to bend forward slightly to avoid collisions as they run. In this next demo, without any constraints, our model outputs a plausible variety of heights where the character picks up and sets down a box. But let's say we want the character to pick up the box at the same location as the source motion. We achieve this by adding joint position constraints when the character picks up the box. So this gives a natural bending motion for the tall target character. We can add a similar hand position constraint on the place down motion to match the source in both of these places. Finally, what if the user doesn't want this back leg to bend as much on the target character? Well, in addition to positions, we can also constrain joint rotations to match the source. So if we constrain the rotation of the back leg, we can achieve an output more similar to the source motion as desired. The iterative process of continually refining the retargeting with constraints makes the DMP workflow intuitive for users. In the case where the target motion should match the fine-grained details of the source motion, like in the specific dance move here, users can constrain joint rotations for the entire motion, while our generative model plausibly fills in the rest. To achieve these results, we first construct a motion paraphrasing dataset. We start from a large set of motion capture data where the same behavior has been repeatedly performed by multiple actors, giving groups of corresponding motions as shown here. However, training a motion paraphrasing model directly on data that is not temporally aligned can produce unintuitive results for users. To address this, we use dynamic time warping to find optimal corresponding subsequences and retime the motions to improve temporal alignment. This works well to align actions in non-periodic behaviors while maintaining actor-specific details in the performance. It also works to align phases in periodic motions like walking down stairs. This allows the retargeting model to learn semantic correspondences between paraphrased motions. To train a motion paraphrasing model from this dataset, we introduce a novel diffusion architecture. At each denoising step, the model takes in a source motion, target skeleton, and a noisy motion with inpainted constraints. The denoiser then predicts a clean motion on the target skeleton. Please see the paper for full details of the architecture. Our method generates plausible retargeting variations of a source motion on a vastly different target character. While our model generates a diverse set of arm movements, the key semantics of the motion, like the height of the box, are preserved in the retargeted motions. To further refine the retargeting results, our method enables user control through kinematic constraints. In this example, full-body joint keyframes constrain the poses to match the source motion, and the height of the feet are constrained to stay on the box. Compared to baselines, rotation copying outputs incorrect route translations that float above the box. Optimization-based methods ensure the motion follows the constraints, but it can lead to jerky and implausible motions due to the lack of a motion prior. Lastly, SAME tends to lack details from the source motion and is not directable, so users can't use constraints to refine and improve the outputs. In challenging interaction motions like climbing, our model outputs natural motions for the target character but can struggle with fine-grained contacts on the obstacle. This can be easily addressed though by adding constraints on the feet and hand height to match the source motion while encouraging contact with the obstacle. Optimization baselines, on the other hand, tend to produce sudden jerks in movement, especially around contacts. Furthermore, the deterministic same model suffers from a mode averaging effect that causes unrealistic and oversmoothed movements. Next, let's revisit the picking up a box motion we saw earlier, where the hand positions are constrained at the pickup and place down. Compared to the baselines, our approach generates a bending motion for the taller characters to more naturally pick up the box. Due to the diverse training data, our model can handle a variety of body proportions while hitting the same hand position constraints. In this case, the root position is constrained after sitting, giving realistic interactions with the bench. However, for cases with challenging body shapes like this one, unconditioned retargeting can result in undesirable self-penetration of the character mesh. Here we see the left hand of the character collide with the belly. With our method, self-penetration can be resolved by approximating the character geometry and applying guidance for penetration avoidance. Visualized on the original character mesh, the guided result avoids severe self-penetration. Similarly, in this motion showing a person searching their pockets, the challenging self-contacts cause obvious self-penetration. Again, self-penetration guidance can improve the result. Guidance and masked inpainting allow our diffusion model to faithfully follow constraints at test time. In this running motion, they enable following the root trajectory of the source motion. Taking away guidance and relying entirely on inpainting to enforce constraints results in less accurate trajectories. Similarly, not conditioning with masked inpainting and therefore relying entirely on guidance tends to drift from the constraint path. Lastly, we see that unconditional generation without guidance or inpainting does not closely follow the path as expected. Note that for the shorter character, the model outputs plausibly shorter root trajectories compared to the tall character in the source motion. In some cases, our model may not perfectly preserve the important semantics of the source motion. For example, outputs for this drinking motion tend to miss the important relationship between the hand and mouth due to the difference in proportions. However, this can usually be fixed by conditioning our model on constraints. Here, adding a constraint on the spatial relationship between right hand and head gives more semantically plausible drinking motions. To facilitate reproducibility in future research, we construct a second motion paraphrasing dataset from the publicly available BML datasets. This new BML MP dataset contains about 10 hours of motion. After training on this data, our model successfully transfers motions from unseen motion categories to new characters. In this case, the taking a photo motion was not seen during training. Full body joint rotation constraints can be added to more precisely follow the source motion. In this picking up a heavy object example, our model generates diverse initial hand positions when there are no constraints. Hand positions can be constrained to match the source motion if desired. Due to the limited size of the BML MP dataset, the model sometimes struggles to generalize to new types of motion. In this case, walking in a circle was not seen during training, so as the source character continues to turn, the retargeted output motion drifts. To explore the generalization performance of DMP, we evaluated our model on characters with extreme, non-human-like proportions. In this jogging example, we evaluate characters with extreme upper to lower body proportions. Despite the extreme imbalance, the paraphrased motions faithfully reflect running in a circle. The character with shorter legs extends their stride, while the one with longer limbs increases knee flexion. Next, we evaluate characters with asymmetric arm lengths, where the right arm is scaled from 70 to 160% of its normal length. Our model successfully handles arm length variations up to 30%, reasonably paraphrasing this throwing motion. However, as shown by the rightmost character, model performance is limited under extreme out-of-distribution asymmetry. Finally, we evaluate characters with irregular upper arm and forearm proportion. Given such imbalanced arm proportions, the paraphrased motion approximately resembles the arm lifting trajectory, but fails to ensure precise hand-to-mouth contact of the drinking motion. By incorporating additional relative joint position constraints, the model achieves proper hand-to-mouth contact, ensuring the core semantics are preserved even under severe body proportion distortion. While DMP achieves plausible motion retargeting under user constraints, minor artifacts such as foot skating or slight constraint deviations can occur. We demonstrate that a simple post-processing step can be applied to further enhance motion quality and constraint accuracy. For instance, the initial DMP result here exhibits slight foot skating at the end. A lightweight foot skate cleanup easily eliminates this artifact. Similarly, in this spin kick motion, post-processing effectively stabilizes the planted foot. Post-processing also improves exact constraint satisfaction. In this box-moving task, the user has specified a position constraint for the pickup and put-down frames. After post-processing, the positional error is reduced from 7.4 cm to 3 cm. In this dance example, arm rotations are constrained throughout the entire sequence. DMP yields a low rotational error of 3.9 degrees, which a light post-processing step further reduces to perfectly zero. It also mitigates minor foot sliding. For this wall climbing motion, position constraints are assigned to the hands and feet. Post-processing reduces the positional deviation on the hands and cleans up foot contacts with the wall. In this box jump example, DMP produces a natural root motion, but the character's feet float above the surface upon landing. By applying post-processing, the character plants accurately onto the box, creating a much more stable result. Thanks for your attention.